Hello everyone. Today we will discuss Littlewood's three principles. As the name suggests, these three principles are named after the mathematician J. Littlewood. So we will start with the statement of Littlewood's three principles. According to J. Littlewood, there are three principles which are roughly expressible in the following statements. The first one is every measurable set of finite measure is nearly a finite union of intervals. The second principle is every measurable function is nearly continuous. The second principle is known as Lewson's theorem. Littlewood's third principle is every convergent sequence of measurable functions is nearly uniformly convergent. The third principle is known as Igruff's theorem. So these are the statements of these three principles. So we will try to prove the Littlewood's first principle. So let us look at the proof of Littlewood's first principle, which says every measurable set is nearly a finite union of intervals. So what is the strategy? How we are going to prove it? We will assume one measurable set whose measure is finite, and then we will try to show that whether this set is, we are able to show this set is a finite union of intervals. So let us begin with its proof. So we will try to proof of Littlewood's first principle. So let E be a measurable set of finite measure, which means that E is a set with whose measure is finite. So since this set has finite measure, so I can write, so its outer measure is also finite. So let epsilon positive be given. So now we have assumed that this set E is a measurable set whose measure is finite. So which further gives its outer measure is finite. So now we are going to use this outer measure quantity. So consider outer measure of given set E plus epsilon. So then corresponding to this, we can find a Lebesgue covering. So then there exists a Lebesgue covering so we all know Lebesgue covering is collection of open intervals. So Lebesgue covering containing in such that n coming from natural numbers. So in's are open intervals such that summation of L of in over n in natural numbers is strictly less than outer measure of E plus epsilon. Okay, so now we can find a positive integer m such that Now, we can find a positive integer m coming from the collection of positive integers such that summation n varying from m plus 1 to infinity L of in is less than epsilon. Let us call it number 1. Now, if we see in this first principle, we wanted to show that every measurable set of finite measure can be expressed as a finite union of intervals. So we are moving in this direction to prove this. So now we consider two sets. So consider, I'm taking one set as O. This is countable union of ions that are coming from this Lebesgue covering. So n coming from natural numbers. So this is countable union of ions. And the second set is, I'm calling it B. This is union ik. So k varying from 1 to m. So here m is the positive integer that I'm taking here. So this m is chosen from this step. Okay. So I have considered two sets O and B. So now one can clearly note that since this collection, is Lebesgue covering for E, therefore my set E is contained in, so I have, so now I know that E is contained inside union of in n in natural numbers. Why so? Because the collection of intervals in is a Lebesgue covering for E. So therefore this happens. So now union of in, this countable union of these ions is called as O. So this means I can call that E is contained inside O. So further, I can write, so E minus B is contained inside O minus B. So I'm removing the set B from E as well as O. So I have this result. So now we know if A is, we know one thing, that if A is subset of B, then outer measure of A is always less than equal to outer measure of B. So this implies outer measure of E minus B is less than equal to outer measure of O minus B. So now further, so if I remove B from O, so I can write. So now if you look at what is my O? O is nothing but countable union of ions. Means I can say this is union from n varying from 1 to infinity. And B is k varying from 1 to m. So if I remove B from A, so I'm left with what? So I can write this as, this is outer measure of union n varying from m plus 1 to infinity In, because my B is nothing but the collection going from 1 to M. So I have removed this collection from 1 to M. So I'm left with, so here I have N varying from 1 to infinity. So I have removed the first M member. So I'm left with from M plus 1 to infinity. So I know all these are intervals. So I can write this is further less than equal to summation N varying from M plus 1 to infinity outer measure of In. So we know one thing, that outer measure of an interval is equal to length of the interval. So this is equal to summation N varying from M plus 1 to infinity. So it is length of In. Why so? Because outer measure of an interval is always equal to length of the interval. So next, according to number 1, we have something. What is that? Summation length of In for n varying from m plus 1 to infinity, it is less than epsilon. So according to number 1, here I have the same quantity, so I can write this is less than epsilon using number 1. So what we have obtained? So from this result, we have got outer measure of E minus B is less than epsilon. So epsilon is chosen to be arbitrary. So since epsilon is arbitrary, so therefore what happens? So since epsilon is arbitrary, so we conclude that E is nearly equal to B. And what is my B? B is actually union n varying from 1 to m, or you can say k varying from 1 to m in. So this is finite union of intervals. So that is, we have proved that, we have proved that E is nearly a finite union of intervals. So this completes the proof of Littlewood's first principle. Thank you.